Hello, everyone. Welcome to the California Dreams seminars, technical seminars. Today, I have the pleasure of inviting Professor Konstantin Sidris. He's an associate professor of electrical and computer engineering and the Andrew and Erna Viterbi Early Career Chair at the University of Southern California. He received his BS, MS, and PhD from Caltech. He was a visiting scholar at UC Berkeley. He was a postdoctoral scholar at Caltech as well. And he's the recipient of ONR IP Award, NSF Career Award, AFSR IP Award, and NSF Graduate Research Fellowship in 2010. Konstantin is working at the interdisciplinary approach. I mean, he has an interdisciplinary approach that bridges applied mathematics, computation, physics, electrical engineering, and medicine to develop next generation technologies. And his current projects explore portable magnetic resonance spectrometers, wearable devices for biological signals, to analyze biological signals, ingestible smart pills, and neural interfaces. And on the computational side, he's pioneering highly efficient algorithms for solving Maxwell's equations. Quite a plethora of research areas, Konstantin. And it's my pleasure to invite you to this talk. And Professor Konstantin Sidris is going to give us a talk on ultrafast inverse design of electromagnetic devices. Welcome, and the stage is yours.
Thank you so much, Ajay. Good afternoon, everyone. Thank you for attending my talk today. And so today I will present to you a recent method that we have developed in my group, which comes from the computational side, but greatly benefits the experimental side of research for accelerating the automated design of electromagnetic devices. So before I get into the main topic of the day, I wanted to spend just a minute or two introducing myself and my research group. Ajay already did a great job with that. So in my group, I have sort of two major research areas. So my research focuses on advancing technology through the understanding and manipulation of electromagnetic fields. And we have a particular emphasis on applications in biomedical as well as wireless communications. My PhD and sort of the reason that there are these two seemingly very disjoint research areas is that my PhD was in analog and RF integrated circuits. And following that, I spent a couple of years as a postdoc in an applied math department working on computational electromagnetics. Since starting my position at USC almost 7 years ago at this point, I have continued research on both of these fronts, and the majority of our projects, as Ajay mentioned, are cross-disciplinary, bridging the fields of electrical engineering, mathematics, applied physics, and medicine. And so on the bottom of the slide, there's just a showcase of some recent projects that we've done in my group, both on the experimental as well as the computational sides. I also would like to acknowledge my team and my sponsors, without whom none of this work would be possible. The photo on the top right is a recent group photo from several months ago in front of the USC Viterbi logo in sunny Los Angeles. So why is the work that we do important? So the chart on the left shows that the energy consumption of several companies has already exceeded that of entire countries. To keep up with the ever-increasing demands on technology by society today, we must develop new holistic co-design methodologies that start at the system level and break down the traditional siloed approach of considering each component, such as digital logic, analog circuit, electromagnetic passives, separately. In my group, we leverage our expertise on both the computational and the experimental areas, which allows us to take a unique perspective in how we approach research problems. There exists a strong synergy between both of these sides. Our computational work is informed and rooted by the practical needs of our experimental projects, and our experimental work likewise benefits from the new numerical methods that we develop. Computational methods enable us to understand electromagnetic fields, whereas integrated circuits offer a powerful platform for us to harness, manipulate, and sense them. Before I get into the main topic of this talk, I wanted to give a very brief overview of some of the other computational work ongoing in my group that unfortunately I won't have the time to discuss today. We have a strong interest in developing new algorithms and solvers that can significantly accelerate the solution of 3D Maxwell's equations while maintaining high accuracy and requiring low to modest amounts of computing power. One major development in this area is in our high order boundary integral equation methods. And I know I apologize, that's a mouthful, which we have accelerated both from an algorithmic standpoint as well as from a hardware standpoint using GPUs. So in the slide here is an example of a Helmholtz scattering problem solved on a personal computer using GPU acceleration. The wingspan of this aircraft is 320 wavelengths, and this discretized problem has almost 6 million unknowns. Each matrix vector product for solving this problem took less than 6 minutes on a standard desktop, taking less than 2 hours to solve the whole complete problem using an inexpensive gaming GPU. One major motivation behind our efforts in high-speed solvers is that we leverage them with and combine them with optimization algorithms to automate the design of new devices. The example on the left is of a nanophotonic 1-to-2 power splitter that we inverse designed using our fast integral equation methods. Since we are also experimentalists, we often also fabricate and experimentally validate our designs in the lab. As you can see, several SEM photos in the middle of devices that we have fabricated. Here's one other example showing the optimization of a non-adiabatic nanophotonic taper, whose purpose is to guide light efficiently from a small waveguide cross-section to a large one while preserving the energy in the fundamental mode. To the best of our knowledge, at the time that this was designed and published, it was the largest silicon photonic device to have been inverse designed using full wave 3D Maxwell solutions, spanning over 65 wavelengths inside the silicon. Okay, so let's get into the main topic today. This is a brief outline of my talk. I will spend the first part introducing the new approach that we have developed for ultra-fast inverse design of complex electromagnetic structures, which we have named the Precomputed Numerical Green Function method. And since that is also a mouthful, I will just be calling it PNGF from now on. And then I will spend the remainder of the time showing several design examples and evaluating the performance of the method. Finally, I will conclude the talk with several remarks, potential future work, and then open up for questions and discussion. So what is inverse design? In the traditional workflow of engineering design, devices are typically iteratively refined by hand by a human designer to improve the performance and meet design targets. This is heavily reliant on human intuition and experience, and is what I call human in the loop approach, because the human proposes an initial design, simulates it. If it meets the requirements, great, but usually it doesn't on the first try, and they have to tweak something, and they have to iterate in this time-consuming loop. Because of this, inverse design proposes algorithmic approaches to optimize devices, basically pulling the human out of the loop. And so the human now, instead of proposing directly at being at the lowest level and tweaking the design at each iteration, the human provides an initial design and target design specifications, as well as potentially design rule constraints. And an optimization algorithm replaces the human that used to be in the loop, refining the design at each step, essentially fully automating the design process. So this not only has the potential to significantly reduce design time and design effort, but it can also lead to novel, non-intuitive designs that exceed the limitations of human creativity. So inverse design has actually been around for a very long time in many different fields, as well as in electromagnetics. On the top left is an example of an inverse designed antenna using genetic algorithms by JPL, and this was flown on the space mission back in 2006. On the top right are various examples of inverse design in nanophotonics that use gradient-based adjoint methods. And on the bottom left are some global-based algorithms, such as particle swarm optimization. And in the electromagnetics world, the traditional inverse design approaches are hampered by the resource-heavy and computationally expensive nature of full-wave electromagnetic simulations. Because of this, many techniques and much effort has gone towards reducing this cost And however, such approaches nonetheless still face significant limitations. So for example, the gradient-based adjoint methods leverage the adjoint method to more efficiently compute the gradient for doing gradient-based searches. However, that still requires 2 full-wave electromagnetic simulations each step of the way. And more recently, deep learning has been investigated. So machine learning and AI approaches have been investigated to develop neural network-based surrogate models that can replace the EM solver for evaluating the objective function. Although these neural network-based surrogate models can significantly accelerate evaluating the objective function, they also suffer from a significant number of real drawbacks. One of them is that they require a very large amount of training data to generalize. And this also suffers from the curse of dimensionality. So as the complexity of the problem scales, as the size of the problem, the number of optimization parameters scales, the number of the training data set required for the model to generalize blows up. And furthermore, they are black box models, which means that there are no guarantees that once you have trained the model, that every possible geometric input, basically every candidate design that you present to this model will yield the correct solution on the output, that it will match with the original full wave solver, essentially be the true solution to Maxwell's equations for the device that you presented. So in this talk, I will present the precomputed numerical green function method, or PNGF for short, which we believe can address and solve all of these issues that I just presented. So one key thing to notice when one is doing inverse design is that typically only a small region of the simulation domain is actually being modified during the optimization. For example, in this case, I have a dielectric substrate with these metallic tiles that I'm changing, and you'll see many of the examples we'll show will follow this sort of setup. And in the optimization problem, I'm just changing tiles within this square grid. However, at each stage of the simulation, to evaluate the objective function that I'm trying to optimize, the substrate stays the same, the air box around the substrate remains the same, any sort of absorbing boundary condition such as the perfectly matched layer stays the same. And so oftentimes, very large parts of the design that you have to simulate in order to evaluate the objective function remain static. They're not changing during the optimization. So the PNGF method leverages this characteristic to significantly reduce the problem size. In fact, we'll see that it reduces the problem size that needs to be solved to one that is proportional only to the size of the optimization domain, basically proportional to the number of optimization parameters you have, regardless of the size of the full simulation domain. And this is done through an efficient single-step precomputation phase, which I will explain. And this precomputation should not be confused with training. This is not a neural network model. It does not require a massive data set. And it can be done on a single node in minutes to typically less than an hour. And the other key thing to note is that once this precomputation step has been done and we're ready to actually evaluate candidate designs, electromagnetic designs, it essentially achieves the similar speed as neural network models. However, it is not black box. There are no uncertainties. The accuracy is guaranteed to match that of the solver used to generate the precomputations. So effectively, it maintains the accuracy of a full wave method while achieving the speed of a machine learning or AI-based approach. So some preliminaries. Let's discuss the discretization approach that we will be using for the examples presented in this work. So we will be considering devices whose optimization regions consist of 2D grids of tiles. And each of these tiles can either be filled in with metal or left empty. So these devices can be easily discretized with a number of methods. In these examples, as well as in the paper that's currently in review, but also available on archive for viewing, we discretize using the finite difference method for simplicity. Although one of the examples that I'll show towards the end, we used method of moment solver to do that, to show that we can also do non-Cartesian tiles and meshes. So Electrically thin tiles are modeled as two-dimensional sheets of perfect electrical conductors and with this finite difference method. And one thing that I would like to emphasize is that although we're considering pixelated devices due to the ease of modeling and fabrication in the following examples, the PNGF method is applicable with any alternative discretization scheme. And the concept of tiles is not inherent to the method. In fact, in some ongoing research, we're investigating different types of parametrization approaches for the designs itself, including level set methods. So how does the method work? So it's useful in order to understand this to start with a thought example. And I assume that the folks listening to this to understand everything given the limited amount of time, you may need to have some background in electromagnetics. If you don't understand something, I'd be happy to answer questions later, or the design examples that I will show don't require understanding of all the low-level details to understand. So current equivalence. So let's start with a hypothetical example. So it would be really nice and convenient if somehow we could simulate one tile in our tile grid of our optimization being filled with metal at a time, get the objective function, and then essentially simulate every possible tile being on with one tile at a time and all the other tiles being open and not filled with metal. And then if we have any arbitrary during our optimization, if we have any arbitrary combination of metal tiles to form some sort of electromagnetic structure, take this basis set of solutions that we pre-simulated, take a linear combination of them to get the objective function value due to that without having to run a new simulation. Of course, those of you well-versed in electromagnetics know that this is clearly not possible. And the reason for this is that metals scatter fields. And so therefore, if I just have single metal tile solutions, they won't capture the multiple scattering that will happen out of the combined solution with multiple metal tiles being on. However, on the right here, we have we have current densities, and current densities actually are transparent to each other, meaning that if I simulate a current density and I get the fields due to that current density, due to linearity and additivity or superposition of Maxwell's equations, I can simulate a different current density and domain without the original one, get the fields, and then I can linearly combine these fields and get the exact same solution as if I had simulated both of these current densities together. So this sort of presents a sketch of an idea, which is that instead of pre-simulating metal tiles, we can actually pre-simulate current densities. And then based on the current equivalence theorem, there's a surface current equivalence theorem of Maxwell's equation, which is the foundational basis of integral equation methods. But based on current equivalence, we can actually find the amplitudes for the currents that are needed to satisfy the boundary conditions for Maxwell's equations and result in exactly the same fields as if we had simulated the metallic problem wherever we had these current densities. So for a given design, what we need to do if we, for example, want to represent these pieces of metal for some sort of incident field is that we need to find the coefficients for the co-located current densities wherever there are pieces of metal, such that the combined fields produced by these current densities, summed with the incident field, satisfy the boundary conditions of Maxwell's equations, which for metals, for perfect electrical conductors, those boundary conditions are that the tangential electric field on those pieces of metal is identically zero. And so essentially what this results in is a linear system of equations where we essentially our unknowns are these current densities that are located wherever we have pieces of metal. And our right-hand side is minus the incident field. And then the matrix itself corresponds to the solutions mapping that we've pre-computed with these simulations that I mentioned, which map each of these components of the current density to the total scattered electric field over the surface. And so by solving that system of equations, which keep in mind, as I mentioned, is only proportional to the size of the optimization region, because we only need to have these current sources wherever we have pieces of metal, we can find the equivalent currents that would satisfy Maxwell's equations. And now by uniqueness of Maxwell's equations, we actually have solved the same exact problem that we would have if we had implemented the piece of metal directly as material parameters. So what we're effectively doing here is we are effectively using a numerical greens function for the optimization domain. And so because of the fact that it's a numerical greens function, it means that the surrounding, and we're using an electromagnetic solver to compute that, it means that the surrounding environment can be anything. It's not limited to open free space. It's not limited to layered substrates. It could be finite circuit boards. It could be different chips. It could be chips on circuit boards. The limits are essentially just your computational power available and in the bounds of your imagination, essentially. Okay, so I don't have the time, most likely, to go through every little detail in the derivation, although it is in this paper that is, I mentioned, currently in review, but is available on archive and in the paper as well as a supplementary material. And so I encourage, if you want to look at all the low-level details and in terms of the derivation of the equations and how everything works, to please take a look at this paper. But the linear system, essentially, that we obtain and we solve, once we discretize it, this linear system in the continuous sense actually corresponds to an electric field volume integral equation, for those of you that may have a background in computational electromagnetics or may have heard of integral equation methods. So once the design is discretized, it's encoded into this matrix P, which is a diagonal indicator matrix. So this P matrix, essentially, this G is our precomputed numerical Green's function. It's a matrix which is proportional to the size of the optimization domain. This is just the identity matrix. And this P matrix is a diagonal matrix of ones and zeros, where a 1 corresponds to a piece of metal being present, and a 0 corresponds to it being open. So essentially, if I have a particular configuration, that allows me to map this configuration to my diagonal P matrix. Then I solve the system for the J's. And once I have the J's, I've solved the problem. I can compute my objective function. I can compute the fields everywhere, no approximations being made. So this system has n opt unknowns, where n opt is, again, the number of unknowns in your optimization region, which is typically much, much smaller than n sim, which is the overall size of the simulation region that includes things like the substrate and other things that are not changing, that are not being optimized. In the finite difference scenario, this G matrix maps the Yee cell J elements that discretize the optimization region to the collocated tangential electric fields within that optimization region. So how does the precomputation work? Well, the numerical green function that I mentioned, the NGF, it needs to only be precomputed once for a given design environment. So if I have a particular layered substrate for a chip and I'm trying to design a matching network, or I'm trying to design an antenna on a printed circuit board, and I want different types of antennas, then I only have to do this pre-simulation, this pre-computation step once. I only have to redo it if I change my design environment, if I change my printed circuit board substrate, or I change some parameters of my chip. Maybe I go to a different design process node, for example, or something like that. Once I've pre-computed this green function for the same static domain, I can use it for any number of optimizations. I can optimize completely different devices. There's no training or anything like that's needed. To obtain this G, we need to solve the system at each location where we have a current. Again, in the finite difference world, this would be each Yee cell in the optimization region corresponding to our tile map, and record the collocated electric fields within these Yee cells on the tile map, as well as a small caveat, recording any fields that are needed to compute the objective function of interest, but that doesn't add any additional cost. So this pre-computation can be also efficiently performed in a single step using a sparse direct solver. If you use the finite difference frequency domain method, which we've used for the first 3 examples that I'll show today. This can obtain G with a single run. And in general, a direct solver finds the inverse of this matrix A, which is the finite difference frequency domain discretized Maxwell operator. So, however, we don't need the full inverse of A. we actually just need the mapping from the J's in the optimization region, the currents in the optimization region, to the corresponding E's within the optimization region. And so to define this more precisely mathematically, we define a projection matrix B, which is a matrix that just has ones and zeros. It is a tall matrix, and so it maps J opt, which is the small vector that corresponds to just the ordered J's inside the small optimization region. It expands that and plugs those into the right locations in JSIM, which is the full simulation vector corresponding to the discretized domain A. So then, by definition, the transpose of this matrix, B transpose, can now actually take the full simulation fields that, after solving it with A inverse, E sim, and extract the E field components, E opt, within this optimization domain. And so if you put these together, you get B transpose A inverse B, which maps J opt, which is the J inside the optimization domain, to E opt, which is the E fields co-located in that domain. And by definition, the way we defined the G matrix, this is exactly our numerical green function matrix G. So this is what we need to compute. So I'm not going to get into all the details of the fast method that we use to compute this. It's based on a method from a colleague of mine, Professor Wei Chu, who developed this augmented partial factorization method that can reduce the required memory significantly if you need just the Schur complement for this augmented system. So we create the system where A is the full FD matrix, and you have these B matrices here, and you put a 0 in this location. And if you just do a partial factorization, what you get as the Schur complement is minus the G matrix. And so it turns out, and again, please take a look at Professor Wei Chu's paper for more information on how this works and why it is so effective. But it allows you to very efficiently, with low amounts of memory, compute this G that we need in a single shot. So an additional optimization that we can do that significantly accelerates the method further is actually based on the optimization algorithm and technique that is leveraged that we often use to optimize these devices. So I'll explain how that works a little bit. And so for all of these examples that I will show today, we used an algorithm called direct binary search, DBS. It is quite simple. I can probably explain it in a single sentence. And so the way that DBS works is you start with an initial solution. You choose a random tile and flip that tile. If that improves your objective function, you keep that flip. If it doesn't improve your objective function, you undo that flip because it was a bad idea, and then you choose another random tile. And you keep flipping tiles using this approach until you reach a local minimum where there are no more tiles that can be flipped to improve the objective function. It's quite simple. It seems like a very naive method, and it is, but it actually in practice works very effectively for these metallic optimization problems. One thing to keep in mind about how this method works is at each iteration of the optimization, it creates a very sparse change in the domain. Basically, one or a few tiles flip. It doesn't change every single part of your optimization change. So it's a sparse change, which corresponds to a low rank change in the matrix system that we are trying to solve, the inverse of that system. So compared to a gradient-based optimization, for example, where you change the whole domain, this method is sparse. And so PNGF already achieves significant acceleration in terms of not having to resimulate the whole design, which is proportional to n sim. We just have to invert a matrix which is proportional to n opt. But we can also leverage the fact that our updates are sparse to accelerate this significantly further, as I mentioned. And so since the update is sparse, we can actually store the inverse of this matrix that I mentioned, this matrix that I have here, the I minus P plus PG, where again, P is the diagonal matrix that corresponds to where you have metals in your domain. And so we have the inverse of this matrix, which was what we need to compute at the beginning. And if we were going to be doing this and changing every parameter, then we would have to, if we would completely change P, we would have to invert C naught again to compute the objective function again. And then this cost would again be proportional to n opt cubed if we were solving a dense system of linear equations. However, since we're only making a very sparse change to our grid, we're only perturbing this P matrix by a few elements. And if we have the inverse of C, we can use a very well-known mathematical formula for low-rank updates called the Woodbury matrix identity. And so I again don't think I have the time to like explain sort of the computational complexity of using this Woodbury identity to do the update. However, the sort of take homes from this are that if you want to update the whole matrix, you want to change the tile and update the whole matrix inverse that you have, instead of n opt cubed, now it's proportional to n opt squared. And perhaps more surprisingly or importantly, if you just want to evaluate the objective function due to flipping a tile, but not yet update the matrix because maybe that tile flip was bad and you want to undo it, so you want to go back to where you were before, you can show that this can be done in linear complexity, order n opt. So basically, it's the fastest possible complexity that you can have for something like this. And the reason that this is so important is that with these random-based methods where you're flipping a tile at random, a very large proportion of your tile flips are going to be bad ideas, bad flips, essentially, that you'll have to undo. In fact, likely more than 90% of your flips you're going to undo and not have to update this matrix. This matrix only gets updated when you have a good flip. And so the overall complexity of the method is some sort of average of this order n opt and order n opt squared, but it's much closer to n opt because most of your flips you undo. So let's start getting into some results. The first, at the beginning, before we do some real design examples, we consider a few sort of contrived toy examples to validate the theoretical expected performance of the PNGF method. And so in the first case, we construct a design comprising an optimization region on the top surface of a substrate with a ground plane. And we look at the time needed to evaluate the objective function for two cases. And the objective function is basically due to a tile flip. So we're going to flip a tile in the optimization region and measure how much time it took to evaluate our objective function, which is, in this case, computing the electric field at some point, or I think it's computing the S11 for an input at the source input for this tile map. And so the first scenario is we're going to fix the optimization region size, and we're going to be increasing the size of the simulation region. So we're going to be increasing the PCB size or the chip size, the dielectric region essentially, as well as surrounding airbox and everything else. So what this is going to result in is increasing nsim, but nopt stays the same, which is the region that we're actually going to be optimizing. And based on what I told you with the PNGF method, the present method being described, this should result in constant time complexity because, as I mentioned, the cost of the method only depends on the size of the optimization region, whereas if you're using a full wave EM solver, the cost of that method is going to be growing based on the complexity of that EM solver, because the EM solver, at each time you flip a tile, needs to resolve the whole system electromagnetic environment from scratch. And then the other example that we will consider is we will fix nsim and we'll grow the size of the simulation environment, the optimization environment, excuse me. And in this case, we're fixing nsim and growing nopt. And we should see that flipping a tile, based on what I said earlier, we expect that to have linear time complexity, order nopt, because we're just checking the objective function for a tile flip. So here we have the results. On the left, we have the experiment where we're growing the substrate size. So basically, we're growing the simulation size, but we're just keeping the optimization region to half a wavelength by half a wavelength. And we have a number of commercial as well as homebrewed solvers, full wave solvers here. And you can see that the complexity or the evaluation time for the tile flip increases pretty substantially as we grow the simulation size, despite the optimization region size staying constant. Whereas with the PNGF method, it stays completely flat, as we expect, no changes. And then for this largest size here, we have 1 million times faster performance using the PNGF method versus using something like HFSS or CST, which are well-known, highly optimized commercial solvers. On the right here, we have PNGF with 1 core with 128 cores. The reason that we did the 1 core is to show that more basically, that to show that the linear trend is actually satisfied, matches the theoretical expectations. The higher number of core, the more parallelized solution, it appears sublinear. The reason for that is that for the smaller problems, the full number of cores, which we use the server with 128 cores here, we're not able to be used as efficiently as with the larger problems. And so it seems like you're getting faster performance as you increase the size of the problem, but it's not due to the algorithm. It's just due to the fact that you're better utilizing the hardware that you have available. And so to show a fair comparison, to show the true trend, we also had the single core example here as well, showing that indeed the time complexity is order and opt. As your optimization region grows in size, the complexity to flip it, the time that it takes to flip a tile only grows linearly. Okay, so let's actually get into some real design examples. So for our first inverse design example, we wanted to design a wideband 30 gigahertz substrate antenna. So we have a finite printed circuit board substrate. You can see the dimensions here are 10.5 millimeters by 10.5 millimeters with about 1.4 millimeter thickness and a ground plane on the bottom. We have a lumped port at the center driving the structure. And the substrate that we used is Rogers 3035, which has a dielectric permittivity of about 3.5. And so our optimization goals here are to maximize the S11 bandwidth and also maximize the gain across that bandwidth range in the broadside direction. And so here I will show an animation that shows the optimization process happening, and the timing of the frames of this animation has been adjusted so that effectively it takes the same similar amount of time to play this animation as it takes to optimize the antenna. So you can consider this basically like a live or a real-time design, essentially. So this is flipping the tiles. This is actually how long it takes to evaluate the tile flips for each tile flip. If you were using something like a commercial EM simulator, it would take at least several to tens of minutes to evaluate each tile flip rather than milliseconds, and it's done, by the way. So this is the final antenna design. You could see that the S11 bandwidth here is more than 10 gigahertz. I think actually in the next page, I'll show the parameters across a wider range. So you see that this is a very broadband antenna going from below 25 gigahertz to above 35 gigahertz. And one thing to note, and then I'll show it more quantitatively on the next slide, is that this dotted line is using a finite difference time domain solver to be able to simulate a broadband response that was simulated on the same discretized finite difference grid, on the same Y grid that we use to get the precomputations for the PNGF method. And you can see that the predictions from the PNGF method fall exactly on top of the finite difference time domain simulation. And of course, for verification, we used an extremely refined grid with HFSS to show that, indeed, this design is electromagnetically sound. And on the right here, we also show the radiation patterns at each of these frequencies. To be a little bit more quantitative in terms of the predicted objective function parameters by the PNGF method versus the solver used, the finite difference frequency domain solver used to do the precomputation. If we take the final design that we optimized and we look at PNGF's prediction versus based on the tile flips that we did, versus if we just put it into our EM solver, we put that EM design with the material parameters. These are the S11s and the gains. You could see that the relative error between the two matched to more than 10 digits of accuracy. So there is no uncertainty in terms of we give it some possible input and you potentially can get the wrong output as compared with a full wave electromagnetic solver. Okay, let's look at another design example. This is also a 30 gigahertz antenna, but we wanted to do something a little bit more complicated here. This is a switched beam antenna. So we use a similar substrate, also the same Rogers material, except now we have a lump port at the edge to make it more practical for driving and for fabricating the actual thing, experimentally demonstrating it. And on the other edge, we have a shorting switch where we wanted to design an antenna such that if this switch is left open or shorted, the far field beam pattern rotates in completely from one direction to the other. So this is the finalized design that we had. This one we actually fabricated and measured experimentally. And one thing to note here is that we scaled up the design by 5 times. to be at around 6 gigahertz. And the reason for that was due to limitations on the lab and measurement side of things. And so here are the results. For both the switch on and the switch off states, the bandwidth is approximately 1.7 gigahertz when scaled up to 30 gigahertz. And the performance does degrade a little bit due to the connectors in the measured results. So when we simulated and designed this antenna, we designed it with a lump port rather than an SMA connector. And the SMA connector does actually perturb a little bit the matching as well as the radiation pattern. However, in a future design, we can fully consider the connector in the precomputation. So this is not a limitation of the method. It's more so a limitation of the design approach that we took for this particular example. And you can see that the measured beam separation angle is approximately 70 degrees when you consider the switch on versus the switch off states. To show that, this is a pretty general approach. It's not just useful for antennas. Here is a broadband short length transition from a microstrip line to a substrate integrated waveguide. And normally, the way that you would do this would be that you would use a very long adiabatic linear taper. And so here we wanted to see if we could do it in considerably shorter length than you would need for a taper to be efficient. And so this design is actually less than 1/3 of the length of the taper that you would need to get a similar bandwidth. And so our structure here is symmetric with microstrip line feeds and 50 ohm lump ports at each end. And the two optimization regions are identical. So we're trying to optimize the S12 through this region with these mode converters on each side. So this is the finalized design. This is the structure that we have. It's this pixelated structure. It looks very non-conventional. It's basically a straight microstrip line and a bunch of these flip tile pixels. It really looks like it probably shouldn't work, but we fabricated it and we measured it, and it actually ends up working quite well. And so the 10 dB bandwidth is almost 8 gigahertz, and the insertion loss is actually less because it's so much shorter than if you had used that adiabatic taper. So let's look at some timings. Let's look at, because I haven't showed timings, I just showed sort of like the actual devices and their EM performance, but let's see how expensive, how long it took to design these devices. So if we compare the PNGF method used with the DBS optimizer using against HFSS and CST, the PNGF dramatically accelerates the overall design process, as we can see here. So the average iteration time for these, all of these designs is significantly less than a second. In fact, for the switch beam antenna, it was only 12 milliseconds for each tile flip on average. And the optimization phase, you could see here, the most expensive one, because there were the most tiles required more tile flips, was still just over 2 minutes for the substrate integrated waveguide and less than half a minute for the switch beam antenna. And then the precomputation time, which I mentioned should not be confused with requiring a training data set. It's not a training data set. It's really just a precomputation. You can see here for these smaller examples was under 10 minutes, and here was just over an hour. And the reason that it was so much larger is because we actually simulated a full long substrate integrated waveguide. So the simulation problem was larger, but nonetheless, it still took less than 2 hours, basically an hour and 23 minutes on a single node on a single machine. It wasn't distributed across, it was just CPU. It wasn't even GPU accelerated. And all of these, I should mention, by the way, these are CPU results. We plan to GPU accelerate this to get even more speedups, but they have not been GPU accelerated yet. And you can see here that the speed up compared to using commercial solver is upwards of 1000x. In fact, for the switch beam antenna, it would have taken almost more than 16,000 times longer if you had used a commercial EM solver each time you did a tile flip to resimulate the design. So in terms of some additional results that we have gotten recently, this is to show that you're not just limited to Cartesian tiles or square tiles or finite difference methods. So here we actually used a method of moments solver to do the precomputation to get the precomputation matrix. And we actually also showed that we can do multiple layers. So it's not like the previous designs were single layer, but that was just based on the design examples that we had chosen. To show that we're not limited to single layer, here we have a substrate where the dimensions are shown here. And we optimize both the top and the bottom sides of the substrate concurrently to create a metasurface beamformer. So we have a plane wave coming in, and the plane wave basically creates a narrow pencil beam on the output. So this took the precomputation, again, took less than a minute and a half. And the optimization time, once we had that precomputation, took less than a minute, just 45 seconds. Compared to if we had used that same MOM solver that we used to get the precomputation to do the optimization itself, basically re-optimize the design rather than use the PNGF method, this was more than 8,000 times faster. This is unpublished work, but it's just some preliminary design examples that we've been extending this also to other domains. So we're also looking at nanophotonics, where our tiles now are not metals, but they're dielectrics. So the method itself is certainly not limited to metallic structures. It can be extended to many different types of physics. Here we have a 1 to 2 nanophotonic splitter. This only took 10 seconds to design on a laptop computer. It's 400 times faster than if you had used an FDFD method to simulate the structure. And here is just one more example where we used the PNGF method to design a symmetric broadband directional coupler that has more than 100 nanometers of bandwidth using this sort of, I like calling them QR coded approaches, essentially, where you have these tiles that you flip. And this took 6 minutes to design on a laptop computer. At every frequency point, the total transmission bandwidth is more than 97.5%. And it would have taken more than 150 hours to design using FDFD or 84 hours using commercial FDTD solver. And this corresponds to 1500 and 850x speedups, respectively. Okay, so to conclude the talk, in terms of where I'd like to see this research go, where I see this headed, I would like to develop a framework that can be used to automate the synthesis of generalized electromagnetic devices based on a high-level description language of sorts, such as an EM description language, EMDL, combining passive electromagnetic components, active circuits, and even digital circuits, and co-optimizing everything. So this is clearly a very challenging problem, but there's lots of room for exciting developments and collaborations in this space. So in conclusion, I have presented a recent ultrafast approach that we have developed for electromagnetic inverse design. It involves a single precomputation step, which does not require any full wave simulations or full wave solves following that to do subsequent optimization runs. No approximations are being made here. The accuracy matches that of the full wave solver used for the precomputations. And it takes generally on the time scale of seconds to minutes to optimize high performance devices. In future work, we'd like to generalize this to dielectric optimization problems, as I've shown for the nanophotonics. We've gotten a head start in that area already, using alternate solvers like MOM or finite element methods of the precomputation, as well as accelerating this even further to hardware and GPU platforms. Furthermore, we'd like to actually use these to do active RFIC co-design with active passive co-design and develop complicated multi-block systems. So that concludes my talk. It looks like hopefully I'm right on time and have left enough time for discussion and questions. For everyone that has managed to stay through till the end, thank you so much. I really appreciate your time.
Thank you, Konstantin. Great presentation and great results as well. We have a few questions here. Let me read these questions, or maybe if Milan Monke is there, you can come up to the mic and then ask the question. Otherwise, I can ask the question that you have written here. Milan?
Hello. Hi, can you hear me?
Yes.
Hi, yeah, a really interesting talk. Really fascinating work to see state of the art in computational electromagnetics and solvers. I had a few questions regarding benchmarking. Have you done any benchmarks related to other solvers like EMX, Momentum, for like microwave passive circuits? That's one question. And then second question is, have you seen like how does the sort of like solver compare to like when you accelerate with GPUs? And can you do like mimic inductors and balance with these?
Absolutely. So I'll answer the first question. So um, we have used EMX for some designs. The EMX is a little limited in terms of what you can do because it assumes an infinite layer medium essentially. So you can't have finite substrates. So you can't. Many of the designs that I showed here, you actually would not be able to simulate at all with EMX. So for designs that you can simulate with EMX, you still get a pretty significant speed up in comparison. I don't have results to show you right now off on my current slide deck, but the FICO results that we had, which we used FICO as the precomputation, is a method of moment solver. So the algorithm is very similar to momentum in EMX that's used to solve. And it's similar speed, maybe a little bit slower than EMX per se, but and compared to this, we're getting more than 8,000 times speed up using a solver like that, for example. So the improvement can be pretty significant. And it comes from the fact that once you do that precomputation step, you actually are now solving the time complexity is significantly reduced. It's basically just order the number of unknowns in your optimization region, and there's essentially almost no possible way that you could speed it up faster than that. In your question in the chat, you also mentioned surrogate models. It's actually that it's harder to do like an apples to apples comparison because and this is going to go into the answer for your next question, is we have not GPU accelerated this yet. This is actually one of the directions, as I mentioned in my conclusion, that we'd like to go into next, because the matrix operations that are required to compute the tile flip, essentially, they're really sort of matrix vector operations that can be, it's what GPUs essentially are really adept at doing. So GPUs are great at doing this. So we expect to see a significant acceleration further. And so, surrogate models running on a GPU, it's not really a fair comparison against our model or our system running on CPU. But nonetheless, like it's similar. Like as you saw it in this thing here, it takes 12 milliseconds to evaluate a tile flip for this sort of thing. And on the GPU, on a surrogate model, I mean, again, it depends on what GPU, what surrogate model, and what are you doing. So it's kind of hard to do an apples to apples type of system. I had one of my students, he was actually looking at some surrogate models, neural network based models. And one issue with those that we've sort of struggled with is that the amount of training data that you need to really generalize goes into the millions of training examples. And so the way that people get those is by doing EM simulations, and it can take weeks to get these EM simulations. And so that's why, and then finally, even if you have generalized it for your training and test data set, when you're doing the optimization, it's possible that you give it some example where the surrogate model predicts that, hey, this is going to work great, it's going to be awesome. And then you take that design and you're pretty excited about it and you put it in your EM simulator and it just doesn't work at all. And so we've seen that quite a bit with some of these neural network based models. Regarding the last part of your question, where you asked about can you simulate inductors or other passives? Yes, absolutely. The only limitations are those of the EM solver that you're using to do the precomputation. And so if you can simulate those passives using whatever full wave solver of choice, a finite element method or finite difference method, or a method of moments like EMX or FICO or whatever, then you could use PNGF on top of that. So there's no inherent limitation in the method itself. Does that answer your questions? I'm not sure if I missed one or.
Yeah, no, that's pretty insightful. Answers all of the questions. Actually, I had one more question, if you will. Is this sort of like a solver or a method available as like a library that people can use, or what is the plan for
Yeah. So currently the paper's in revision. We have a cleaned up sort of example code that we are trying to find sort of what's the best way to make it available. So open source is one option. There's some sort of potential issues around that. Currently, I'm trying to find potential industry collaborators to evaluate this on different process nodes for different technology nodes for ICs and RFICs and so on. And in particular, there's some CA Dreams related RFPs coming out soon that I'm interested in teaming up with folks and exploring that domain. But we're trying to find sort of what's the best way to share this with the community, essentially.
Definitely, yeah. Happy to talk more on that. Thank you.
Yeah.
Thank you, Milan.
So, Milan, you can send me an email. I don't know what your affiliation is. Are you academic or industry or?
I'm the founder of a company called ZapRF. We are automating
Okay.
mimic design.
Awesome. Okay. Please reach out to me. Would love to
Sure.
start a conversation.
Sure.
The next question is a generic question. The question is, what is the difference of inverse design versus classic optimization? And that's probably, you might have explained it in the beginning.
I think, now we're maybe getting a little bit into philosophy.
Yes.
So I personally don't think there's much of a difference. I think that inverse design is a nice term that has been coined some years ago to sort of represent that instead of doing in design in the forward way where you present a design and you evaluate the performance, you give the performance that you want and the algorithm gives you a design. But the algorithm within that is an optimization algorithm typically. So I think it just depends on your viewpoint. Some people might have stronger feelings about this than I do, but I often use the two terms interchangeably myself.
Thanks, Konstantin. The next question is, how would your method be affected if you take into account loss tangent for low values of 0.001 and also for high values like 0.01?
Yeah, so actually it doesn't get affected at all. As I mentioned, the accuracy and fidelity of what you can simulate is purely depends on the solver that you use to do the precomputation. And so in the simple example that I showed, we just did PECs where we just have to satisfy that you have the zero boundary condition. However, if you want to incorporate loss tangent, if you have lossy metals, you could simply treat them as dielectrics. And so we have the formulation does not increase in cost or complexity to change a complex epsilon rather than assuming that the conductivity is infinite. So it works just fine. We've done that before. In fact, we are currently investigating, and this is completely unpublished work, and I don't have any results to show, but we have promising results that I can't show yet because they're very, very preliminary. But we're incorporating full stack-ups for various processes, for semiconductor processes that include the full the metal thicknesses and losses and everything to get very accurate simulations within this optimization framework.
Thanks, Konstantin. The next question, maybe I have something to add to it. It is about metal thickness and metal thickness of real PCBs. That will pose difficulty to this method. And also, how is it Q sensitive, especially for the passive inductor designs, where the HFSS simulations used for benchmarking used zero thickness metals as well. And one question which I have here is, have you considered metal thickness or the surface roughness to your simulations?
Yes, these are all great questions. So in the examples where we use the finite difference frequency domain solver, it's really difficult to get very thin metals represented with finite differences, just because the complexity of the method increases and you have a Cartesian grid. So for those, we just assume that you have like a single sort of flat surface, and we tried to make the DZ such that it matched sort of what the metal thickness would be. In the corresponding HFSS simulations where we compared it, we actually used the true metal thickness of the PCB that we're going to fabricate, just to make sure that the design we fabricated should actually hopefully match, and those did match pretty well. However, in the most recent work that we're doing, where we're using true mesh-based methods, we're using method of moments integral equation-based solvers for precomputations, we are fully representing the 3D metallic structure and the thickness and the loss and everything of that. So that is being accurately represented in the 3D electromagnetic solver. To answer your question about the surface roughness, we don't have a particular surface roughness model that we're considering. However, typically oftentimes we'll consider surface roughness as an additional loss. And so if you have a way to map the surface roughness to sort of effective epsilon or conductivity parameters, then we can very easily already map that into what we already have. If you have a different way of representing surface roughness, then please talk to me. I would love to learn more and see if there's some way that we can extend our method to consider that further.
Okay, great. Thanks. And then we have another question from Tariq, which is about curves and tapers such as Vivaldi quad ridge horns or parabolic reflectors. By the way, it's already 4 o'clock. We have gone past that. We are soon going past the time. I hope you can stay, Constantine. You
I
have
can
another
stay
2
extra.
moments.
Yes,
You
I
can
have
stay.
time.
Okay.
Yes, yeah.
Okay, good.
So I apologize if I'm starting to sound like a broken record, but so curved structures are more challenging with finite difference methods. But if you use a mesh-based method, like a finite element method or a method of moment, where you actually have you don't have a structured mesh, then you could represent those fairly readily, and you could have curved structures without problem. You just need to discretize the curve. You can use curvilinear elements if you want. We haven't done that, but you can do that. The majority of solvers, including HFSS and CST, they essentially just discretize the curves in terms of piecewise linear segments. You could do that as well, to whatever fidelity that you need. So the underlying optimization method and the acceleration, the PNGF acceleration, again, does not set anything. It doesn't constrain anything about the grid that you use. It only has to be a Cartesian grid if you use the finite difference-based solver to begin with, which we did in our initial examples because it's the simplest kind of solver, and it's also an easy way to demonstrate how the method works and to explain it.
Okay, so if there are any more questions, please contact Constantine directly. You have his email address, which was actually shown. Amy, you can actually share the slide that you have. It's gone 4 past. Amy, there are 2 more questions too.
Yeah. Oh,
Yeah,
I can answer more if you'd like me to answer more questions. But my email is just csideris@usc.edu. If for anybody that would like to reach out to me for further discussions.
Yes. So I thank you again, once again, Constantine. I mean, since it has gone past 4, I mean, I don't want to take your time too much. But thank you so much. And it was a great presentation and great participation from the audience as well. So many questions. Even I have several questions which I didn't ask. I mean, I will probably ask next week.
Please do.
So
Please do.
the next week's presentation is from UC Riverside, Professor Luat Wong. It's again on optical sensors. And we are looking forward to it as well. Thank you so much once again. And thank you all for attending this technical seminar.
Thank you, everyone. Very much appreciate it.